too many things going on. And then I need to start sharing my screen. Okay, so I use a whiteboard. And I believe we have the last part not finished yet conceptually. Okay, then we will go to coding. And I believe regarding the general concept about, so what over here we did binary search tree, okay. Maybe I change the olive green color. Okay, I like it because it looks like you are viewing some trees when we do the drawing. Okay, so what we discuss is binary search tree, is it? And the concept I believe you all already know, is it? Left subtree is less than the node, is it? And the right subtree is greater than the node, is it? So we discuss how to create a tree. Generally, we write as BST, is it? And how we do insert, is it? Insert new item to BST, is it? And also try to do search, how to search an item, is it? On a BST, as a binary search tree, is it? And we also discuss traversing. And traversing, we discuss three kind of ways to do traversing: in order traverse, pre-order traverse, and the post-order traverse. And then we discuss all the three ways for traversing. And I think that's all. Is that we haven't discussed delete and remove, is it? Or remove. That's what we are going to discuss today. Okay, but we already have general idea about all of the other topics. So first, so today we will discuss delete an item. Okay, in a BST tree. So let's first take a look at an example of a tree. So we have G, so it may take a while for me to complete drawing the tree. Then we have F, and then we have A.
Dr. Lou?
Uh-huh.
We did delete with one, we just didn't do one with more than one child.
Oh, okay, okay.
We did leaf node delete.
Okay, very good, thank you. Leaf node we discussed, is that okay? Yeah, it's been a while because of snow day. And then we have B here, we have D here, and then we have J here, okay? And then we have H here, we have O here, and we have I here, and we have M here, we have P here, and we have, I don't know why the pen not working. Hold on, okay, let me, sometimes it just stuck there. Okay, then we have M, and we have what? We have K here. After K, we have N here. And we have L here. And also, please help me to double check if this is a binary search tree, okay? If I did something wrong. Looks like okay, yeah. Okay, looks like okay, then maybe I change a different color to highlight. So last class, I believe delete D. That's pretty straightforward, is it? So it's a leaf node, you just delete it, make its parent, so this is parent. Make a parent's right point to a null. That's the delete D. And oh, I did something. I did mess up something. After A, I should have, I'm sorry, okay, here. I should have that E, and C is connected to E, okay. And then we also discuss delete. Did I already complete delete node E, item E? Anyone remember? E.
I think so.
Okay, we already discussed. Okay, so E is also special. Is it because it just has one child? Is it just has one child? And the way to delete it is you connect its child to its parent. Is it? So like that. So that's we already discussed. So this is a leaf node case. This is a case, a node with one child node. Okay, so today what we are discussing is a case. Let's see, delete item J. Item J is here, is it? Is here. And J compared with other, it's special, is it? It has both child nodes. Is it? Then if you apply the previous strategy, it won't work. Is it? It won't work. So the way to do it for this kind of case is the first step is you find its in order successor. It's in order successor. Okay, doesn't mean it's child node. It's in order successor. In order that means when you do in order traversing, what's going to be the next node visited or going to be processed? So we are trying to find its in order successor. Is it? Who is its in order successor? If you then, because it's successor, so it's go to its right subtree. Is it? And right of its in order. Is it? In order is what? It's left node and right. Is it? So you go to then its left. And the following, you go to its left. Is it? So node K, this node is node J's in order successor. Okay, this is its in order successor. So we can write it as in order successor. Successor, is it? So what we are going to do is first find the in order successor, and then we exchange the item contained between these two nodes. Okay, so we swap the contents. So swap contents between J and its in order successor. Okay, so it's K, is it? So we swap, so K, we move it here. Okay, and we move J here. Okay, and after that, this reduced to what? So it's reduced to the case of either leaf node case or single child node case. Is it? So you swap those two. Then swap those two. And so we reduced the case. We reduce the case. Then over here, what we can continue is it has a single child node in this case, J. Is it? So we are going to try to delete it. Delete the in order successor. Is it? Order successor, and then it has one child, right child, is it? And this is a parent node. So we are going to remove it and connect it to the parent child and the child, the parent node and the child node, is it? Okay, and if you re-examine the binary search tree, is it? This way you can maintain. Then in this case, we maintain the BS binary search trees property. We won't destroy it. Is it? If you just do some delete and don't rearrange, it will mess up with the binary search trees basic properties. Left subtree is less than right subtree is greater than. Is it? Then in this case, you can see clearly that it won't destroy. So that's the step how to delete a node with both child nodes. Okay. So what you need to do, you need first to find its in order successor. Is it? Successor, and after that you swap the contents between those two nodes, and after that the case is reduced to either leaf node or single child node case, and then you can delete that child. Okay, then your tree still going to be maintained. Okay, so that's how do we do delete. Okay, so the conceptual part we are done. Okay, so what next we are going to do is we are going to take a look at the coding part. So I'm going to go here, and we start with this simple case. Okay, later on we will also see the example with iterator. Okay, for this one we didn't add iterator in our implementation. So we have the binary search tree, okay, binary search tree, Java, and we also have the testing file, okay. And the example on our course website is Java BST linked way, okay, linked way implementation. Okay, so that's, let's take a look. So the very first thing is we define our binary search tree, and we define as generic. And because binary search tree, whenever you do insert, you need to—
There is a question in chat.
Oh, okay, hold on. Let me clear. Maybe I need to stop. I need to stop here. And let's see. Node somewhere. Oh, we need to go back. Go back to that root node. Okay, that's a very good question. Let's go back to the whiteboard. I'm sorry, I erased that part. Okay, so how about let me get the tree back. Okay, node G. Oh, let me use a different color. How about erase this? It's kind of slow. Okay, don't because it's not like on the whiteboard, the real whiteboard. So node G, and then I have node F. Is it? And I have A here. Hopefully I'm not going to mess up. And then E is here. and then on the left is C. Is it? And it's B and D. Is it B and D? And on the right, it's node J. Okay. And we have H here. And we have I here. And we have O here. And we have M here. And we have P here. And we have K here. And we have N. And we have L. Is that we have L. So let's first maybe let me see. Okay. So in order, is that so here we said we try to find in order successor. Okay, and the in order is left and node and right. That's what's the in order node visiting sequence. Okay, and let's see. We want to delete J. So first, let's make it clear, okay, who is the in order successor? So we want to delete J. This is node going to be later. I'm going to go back to how about the root node. Okay, there is another student said we are supposed to use I, not J. So here we said node J we want to delete, and we want to find the in order successor. Who is the in order? In order successor is if you follow in order traversing the next node to be, so supposing it's outputted, okay. Outputted, is it? Outputted is which node? Node J. So let's see, there is a chat, is it? Okay. So next node to be outputted for J is which node? In order traversing the final output, generally speaking, is what? Is arranged in ascending order. In ascending order, is it? In ascending order after J, then definitely it's going to be K, is it? After K is L, is it L? After L, it's M. After M, it's N, is it? And then after N, it's going to be O, and then P, is it? So in order successor means what's next going to be output for the final in order traversing results. Then clearly we can find it's node K. Then how do we find the in order successor? We go to the nodes right. So go to nodes right. Is it? Then you reach the child node. And then you need to go to the left. Always follow the left. Is it? And then follow left all the way. Is it? All the way until you reach the node. There is no left. That's going to be next visited. Then we know it's node K. Is it? That's this node. Okay, then we swap these two nodes. Okay, so we put J here and put K here. Is it? So then we can do, it's already reduced to single, to either leaf node case or single child node case. Okay, So that's regarding in order successor. Okay, hopefully this is clear. Very good question. How about root node? Is it, how about root node? Root node, the same thing. Is it, suppose let's get back. Okay, let's use eraser. Okay, previously, this is J, is it? Node J. And this is node K. Is it, am I right? Yeah, clear. Node J, node K. And over here, we want to delete G. Is it root node G? So G is similar. G has two, so it doesn't matter it's root node or any node, as you just take a check those three cases. Is it a leaf node? A root node may also be a leaf node if it's a single node tree, etc. Or the tree is unbalanced, then it just has one branch. That's also possible. Then it just has single single child cases, etc. Node cases. And in this case, it has two child, etc. So the same thing, etc. So we need first to find its in order successor. So which is node G's in order successor? Here, anyone can tell?
H.
Very good, it's H. How do we find? We first go to its right child, is it? And then following the right child's left all the way, is it? And over here we reach the node. There is no left, is it? So node H is its in order successor, is it? So you just switch those two. Node G, is it? And then you reduce to the same case. Then you just connect this and delete node G from the tree, is it? You still maintain the tree as a binary search tree, is it? So that's how you delete a. It's not you, but you remove the root node reference from the memory, is it? What memory you remove is this, because what here we care just delete that item. It's not the node itself. It's because we swap the contents. Okay, so here be careful. Okay, so the root node you didn't delete the reference. What you delete is this node. Is it because this node is garbage collection? Is it's not going to be referenced by anything? Is it because the reference in the memory is what? Is only the tree part. Is this part? Is it this part in your main? In your main, if you have a BST object, is it? That object is going to refer this tree, and this node is not going to be referred to by anything. Is it? So it's flowing around. Is it? So that's the it's not you really delete the node. Okay, it's just we swap the contents, then we delete some other nodes. Okay, any other questions regarding how do we do delete? Is the concept kind of clear now? No more questions, it's quiet. So I'm going to go to coding, okay. Okay, so let's take a look regarding the implementation of our binary search tree, okay. And here, I implemented the first approach is I let that T, okay, as bounded generic type. Hold on, I need to get a student coming. So so that's why here I said it, T is the 10th comparable interface. Can you turn off the audio? Comparable because we are going to do compare. It's binary search tree. It's not just a primitive number, etc. So you need to, you cannot just use less than, greater than, etc. You need to also make it support reference type. Please turn off the audio. Okay, then in this case, let's in linked list, if you remember the node at that time, is that we only have a point to the next node, is it? And over here you have two branch, is it? So that's why you have information and you have the left and right. So we call this a bin node. Okay, bin node. And we make the class private because you don't want the outside to the node being exposed, is it? And also we make this is nested class, is it? Inner class concept or nested class. In our previous semester, we discussed, is it? And we make it as static, is it? And make it static, then that means it cannot access the outer classes instance variables, is it? Okay, so over here, we define this bin node. So this is our bin node, and we also make it a generic type T, is it? So it has two parts. Data part, I'm sorry. This should be data part. And it has 2 points. Is it point to left and also point to right? Is it? And the type is also bin node. Okay, bin node. And regarding this bin node class, I also provide a constructor. Okay, make left and right point to node. Okay, and I also have another constructor. It take arguments. Is it take whatever the data and the left and the right? Okay, and then it's going to be initialized with whatever plug-in information. Okay, so this is the basic building unit. Okay, nothing new here. And for our binary search tree, we only have a single instance variable. Okay, root tree. Just like a linked list, you only have the first node. Okay, you only have first node. And for binary search tree, I only have the root node. And the type is the bin node. Okay, bin node. So this is kind of similar as the linked list part. Okay. And then let's see, we have a constructor without any arguments. Then in this case, we just initialize a root node because that's the only instance variable, is it? So we initialize it to a null. So this create an empty BST tree. Then hold on, okay, let me get student coming. Okay, so we create an empty one. So that's root. If you say root to null, that means it's an empty binary search tree. Okay. The second case is with some provided information. That then in this case, you just set to root node to the. So you need to create a bin node. So that's why over here you call new bin node with whatever the item for the node to hold, but it's left and right part. So this is item, is it? So this is going to be your root. And you let its left and right set to no, is it? So that's binary, so constructor, second constructor, okay. And then next, let's see. So we also want to check if the tree is empty. So this is easy to understand, also quite easy. So just do root if it's equal to null, okay? And then next, let's see, search. Hold on. Okay, for search. And search, previously we discussed that if you have a tree, okay, here, and then you can have, so we always start at a root node. At a root node, is it? Then you compare, and then you either move to left or move to right based on the comparison, is it? So compare, compare, and compare. Is that always? So that's how search works. So you're going to see where the item is it? If you can find it. So that's why over here, similar as linked list, we have the cursor. Is it? So we initially set cursor to root node. So this is root node. Is it root node? And over here, we also use a Boolean set false. Okay. So if your cursor haven't reached the leaf node, and if you haven't find the information, is it? So if, because once we find it, we update this as true, is it? Then we can keep going, is it? Keep going. So then you compare item, is it? So if item is equal, and here also, see, we call the equals, is it? Because here it's reference type. Reference type. With the equals, you compare the contents, okay? Not the equal for the shallow copy. This is the deep comparison. You compare with the item is what you are looking for, is it? And here is a current node, as it is a root node. So you compare with the nodes data. And if both are the same, then you set the flag to be true, is it? Then your loop is going to be stopped. So you can directly return, you find it. Okay, here it just care if you can find it, doesn't care where it is. Okay. Okay, otherwise you call the compare to, is it? And if compare to item that compare with data, is it less than? And okay, so how about let's do this as a quiz question. Okay, first quiz question. So where does this compare to come from? Here. So who can figure out why I can call compare to here?
You form comparable.
Yes, because what? Because we said T extends the comparable interface, is it? The comparable interface has a method called compare to. Okay, that's why here you can call, because what? Because item type is T, and T is generic. Generic is extends that comparable interface. Is it? That's why here it can call compare to. Is it? with the data, is it? So you compare those two items. And if it is less than, that means it's less than, you set it to the left. Otherwise, you set to the right, is it? So you are going to keep doing, is it? You either left. So your cursor is going to move, is it? And your cursor is going to move, is it? Move. Okay, so until you reach now, is it? If you reach now, that means what? You didn't find it, is it? So if cursor is now, that means you didn't find it because you cannot update the false, is it? So what you return is still false, okay? So this is a search method. Okay, and then next, let's see. Everyone, please send your quiz answer to the chat, okay? Then it can save you a lot of work so that you don't need to redo the quiz. Okay, and the next is insert. And the insert has a lot of similarity between similarity to search, because you first need to find the node, kind of like the parent node you're going to insert, is it? So similar concept, okay? So we have the cursor, is it? We start at root node. Is it? We start at root node. Cursor, is it? Start at root node. Okay, and then you are just going to, but because later on you are going to insert, suppose here you are going to insert the item. That's where you're going to insert. Is it? Then in this case, hold on, I need to get the student comment. Okay, so when you do insert, it's not you just create a new node, is it? So you create a new bin node. What you also needed to do, you also needed to connect with parent node. Is it connect with parent node? Okay, so that's why we also want to keep tracking of the parent node. Okay, and like here, root doesn't have parent node, is it? So when we moving along the tree, is it? We let parent point to cursor, is it? Because cursor then either go to left or go to right, is it? So assuming we are going to have cursor move down to the left, then this is going to be parent, is it? So it's kind of pair moving, is it? Pair moving whenever you have parent node, is it? But initially you set it to null, okay? So anyway, so first you need to find, and then in this case later on, so I'm going to move cursor here, is it? And here is parent, is it? Here is parent. And when you stop, when cursor is null, or if the item is already in the tree, you're not going to do insertion. Okay, you're not going to do insertion. So if you find the item, you're going to stop moving down the tree, is it? Okay, so you're going to keep moving, and then in this case, parent then going to be updated here, and cursor is going to point to the null node. Is it at that point? Is it? So cursor, and then you can stop. Is it? So you find where it's going to be inserted. Okay. And then next, let's see. I needed to, sorry, I needed to clear this part. Okay. And go back here. So once we find where it is, And of course, if the item is already exist, hold on, I needed to get the student copy. If the item is already in the list, then you don't need to insert, because binary search tree, remember, okay, all of the items in the binary tree, we call them keys, and the keys are unique. They are unique, okay, be careful here. And then we will see where are we going to insert, is it? And we cannot miss the case when the tree is empty. Is it when tree is empty, the parent is null, then you do what? You set bin node. You create the new node, set it to root node. Is it set it to root node? Okay, so that's the root node, okay, single node, okay. Otherwise, what you're going to do, you need to make a decision if the item is greater than, so you're going to compare with the parent node. So this is a parent node. Your cursor point to now at this point, is it? Then in this case, you said I'm going to set parents left to the new node. Otherwise, in our case, it's parents right to the new node, is it? And then you successfully insert it, okay? So whenever we do insert, we first need to locate where you are going to insert, okay? Once you find it, and also here, okay, so how about this going to be the second quiz question? Second quiz question. Okay, second quiz question is in BST, binary search tree, okay? So whenever you do insertion, can you insert anywhere? Can we insert anywhere in the middle? So the I shouldn't. So you still follow BST's property. We still follow left value is less than, right value is greater than. Then when you do insert, can you insert somewhere in the middle of the tree?
No,
So
we
the,
insert anywhere. Since we need to follow the BST, the propric. So always make the left child smaller than root, and the right child greater than root.
Yes, yes. So maybe I didn't make the question clear. My question is, can you insert in the middle of the tree? Can we insert in the middle of the tree? The middle of a tree. Because if you recall for linked list, it's not you just insert at the beginning or insert at the end. You can insert anywhere, is it in the middle also? But for binary search tree, can I also insert in the middle? That's my
No, you
point.
have to make it a new leaf node.
Yes, very good, is it? So we cannot do that. It's always, so binary search tree insertion, always leaf node. Always as leaf node. Okay, so that's the idea, okay. Okay, so that's about insert, okay, insert. And here, we have another called, this search to method, I define it as private. So this is a helper method. Helper method, okay. So what this method is going to do, it's going to serve for delete. because you remember when you do delete, you also need to find where you are going to delete, is it? And then you need to connect, is it? So in that case, we definitely need something to help us to remember a lot of scenarios. So that's why we have the search to, okay? So the search to, the item you're going to search is as one parameter. And here we have an array, okay? We have an array. And for this array, over here it shows, a 2-node array. So the sub-0 is the node containing the item, okay? And the sub-1 is the parent node containing the item. So we are going to kind of need to remember those two information. If you recall for the 2-node case, is that we do need this information, okay? So let's take a look. So node 0 and node sub-0, sub-1, we set to root and null, is it? And then found, okay. And then we are trying to do the search to see where the node is it? And along the way, if you take a look, so both sub-0 and sub-1 going to keep track of where the node is, where the parent node is, okay. So anyway, so this is search 2 going to keep track of the information, okay. And then next, let's take a look at the delete operation. Okay, for this delete operation, because we are going to use that search 2, so that's why here we use this node array, okay. So we are going to call that search 2. We plug in this array so that it will remember if the item is in the tree, where it is, and its parent node, okay? And then we are going to change, just for convenient, okay? We change location to sub-0, and we call the sub-1 as a parent node, Okay, then what next we are going to do is, so we are just going to do the search, kind of, is it to find where the item, oh, over here, we already do search 2, so we already find where the item is it? So this is the where the item, this is a parent node, okay. And then here we deal with the 2-node case. So this is a case 3, is it, with 2 nodes, with 2 child nodes, is it? So location left and the location right. Okay, and then we try to find what? Find the next in order successor, is it? How do we find it? We first go to locations right, is it? At the same time, we need to update the parent node, the parent node update. And then you do what? You keep going left, is it? Keep going left until the left is null, is it? So when you finish this loop, you find where where it's next in order, okay? So this part is find the next in order. Next in order successor. Okay, find the next in order successor. And at the same time, we also keep track of the parent node. Is that a parent node? Okay. And once we find it, is it, we are going to exchange. We are going to update the location. Location is where you, if you recall, where J is. So basically here, you update J's contents to K, is it? That's because this next in order is K, this refer to our case is at K, is it? So I'm going to update location. Is it? I'm going to update the location to K. Is it? It has K. And then I change location also point to the case, the real. So in our case, J is here, is it? And I go to right and then go to left. Is it? Here is that K. Is it? I need to swap the contents. Is it? So I updated here to K. Is it? I don't need to change it because anyway, you're going to delete. Is it? So now this is location. Is it? This is low. And also it has its parent node. Is it? Parent also keep tracking. Is it? So those two information are kept tracked. Okay. Okay, and then we basically reduce the case. Is it? To either a leaf node or a single node case. Is it? So then we can do check if location left is null or location right is null, and we use the child, use this new node to remember where it is. Is it? Because we are going to connect the child node and with the parent node. Is it? So suppose this is a node you're going to delete. Is it? And it has a right. Right. And here is a parent. Parent, is it? And here is that child node. Is it? This is where you want, I'm sorry, that's location. This is a child. Is it? And this is that location. You are going to delete this location, is it? But you're going to connect parent and the child, is it? So that's why I also needed to keep track of the child node, where it is. Is it where it is? Okay, and then over here, is it? You need to also be careful about root node case, is it? So it says if location is root node, and then you need to reset. Okay, you need to reset the root node to child node. Okay, otherwise you just say parent to child. Is it parent to child? Okay, so this is regarding delete. Okay, little bit of more complicated. And what the next one try to show is about the traversing. Okay, the traversing. So first, let's take a look at in order traversing. In order traversing over here, we use a auxiliary, so a helper method. And this helper method implemented as recursion. Recursion, is it? So it's in order, is it? So visit, so the parameter is a bin node, is it? Either go left and go right, and the node, is it? So left node and right, is it? So you recursive call nodes left, nodes right, is it? And you call over here is you get the node, is it? You get the node. Okay, so this is, and what you plug in is what? Is a root node. Root node, is it? And then it's keep a recursive call, okay, in order traversing. So similar, if you take a look for pre-order, it's a similar implementation. Post-order, it's also similar implementation. Okay, so that's the general implementation here. Okay, and then let's see. Let me stop. Let me go back to
I have a
the
question here.
driver. Yeah, please.
What is post order doing? What does it do?
In order, post order. You mean pre-order?
Yeah, like this function. What does it do? What is it doing?
Oh, all those, hold on. Okay. Sorry, go too quick. So in order, we all understand, is it? So this in order is to try to fulfill that. You remember we discussed in order traversing. We discussed traversing. There are 3 types of traversing. You can do in order traversing. You can do pre-order
Oh, I
traversing.
just realized. So it prints out displays the output for the in order.
Yeah. So all
Okay,
this
so-
pre-order post are just output following the traversing order. This makes sense now?
Yeah, I
Okay.
didn't see that there were recursion functions inside.
Yes, I sorry, I didn't realize this. Okay, so pre-order, so that's why we start at root node, is it for the function? Okay, but in pre-order, it should be, yeah, pre-order is node, then left and right, is it? And post-order is left to right, and node is last. Okay. Okay, but anyway, with the implementation over here, we discussed is we use a recursive way to implement. Yeah, so you can clearly see is that if you take hold on, if you compare, you will find for in order the recursive is left node right. Is it for pre-order traversing? It's node left and right. Is it to follow the order? Is it? And then for post order, it's left, right, and node. Is it for the node part? You just output, just have that print statement, but it's a recursive call. Is it? Yeah, so this is regarding the three traversing, okay. And what next? Let's take a look the driver part, and then we will come back to that. We haven't completely finished the binary search tree. Okay, for my testing part, I declare a tree, is it called the new? So initially it's empty, is it the root set to null, okay? And then we read off the data from a file, okay? And we keep getting the number and we call insert to fill the tree, okay, to fill the tree. And what next? What's next? What we do is then we do in order, we do pre-order, we do post-order, is it? And we also testing the delete here. Okay, delete, it asks you to enter a number you want to delete, and then it can be deleted. And you can also double check if the tree, if the item is still in the tree. Okay. And what last it do it going to print the tree by level order. Okay, we will come back later to explain. But anyway, so here is the driver part, pretty straightforward. Okay, so first let me find where that data file is. I will go back to our course website to see if that data file is available. This is on the binary search tree, the data file. Okay, we do have the data file, yeah. Okay, share. So we have that data file, is it? It's kind of not too dark, the color. So that's a plain text file. That's a sequence of number, is it? So we are going to build a tree with this sequence of number, okay? So not a lot of new things here. And we go back to our code, okay? Share screen. And over here, okay, over here. And I'm going to first run this program so that you can take a quick look to see the result. And let's see. Okay, the tree, do we have that? Okay, so anyway, so let's just take a quick look. So here with the running result, it shows in order traversing result, is it, you can clearly see it's ascending order. And the pre-order, is it, and the post order result, is it? So those are the traversing part regarding the tree, is it? Okay, and this part is about, oh, can all of you see my running result screen?
Yes.
Okay, okay. And over here is kind of draw the tree. That's a little bit of complicated, and it's kind of hard to program that you draw like what I hand draw that kind of tree. Okay, it's a little bit of hard because you need to plan where how wide the tree is it? But in case your tree is huge and it's always grow, it's with the program it's a little bit of hard. Okay, that's a very hard question. Okay, maybe you can figure out what's the best way to write horizontal print the tree. Okay. And what over here is kind of vertical, the output. Later on, we will go to the code to take a look how it achieved. So the left, you can take a look. The left go, so over here, it's a left tree and the right tree because it cannot horizontal, is it? So the right tree is the next part. The left tree is the first part, okay? And it follows the nodes, okay? So that's what this part shows. And as I enter a number to delete, suppose I enter what? Suppose let's do 57. And then you see, yeah, 57, did you see it says not in the tree anymore? You can also see that it's not in the tree anymore, okay? And let me quit to see. And if I do the 0, don't delete anymore. And we also have the last kind of output looks like this. Okay, so this basically is what the tree going to 40, 70, is it? And 38 here. 42 here, then 58 here, 75 here, is it? And going on, is it? So if you take a close look, observation, you will find the output is what? Is level by level visit for the binary search tree. Is it first go to the root level, then move to the second level, then move to the third level, then move to the fifth level, is it? Okay, so that's all of the, that's regarding the level output, okay? And then next, let's take a look at the coding part for that level output. How do we do that? Okay, print level. Okay. Print level, is it? And what over here we use Q. We are going to use Q to hold something. Okay, hold something node. And the Q first add what? Add to the root node. As a root node is added to the Q. And then we are going to loop through the Q. Is it loop through the Q? Okay, loop through Q. At this point, the Q size is what? size is 1, is it? So we have 58, and then we have 38, 75, something that I don't remember exactly what it is, okay. But anyway, at this point, the queue size is 1, is it? When it is 1, you go to the loop, is it? Go to the loop, and you are going to do what? You're going to get, so here is your queue. Your queue, you have root node. Is it? You have root node. So you're going to get the root node out. Is it? And output whatever its contents. Is it? And then what do? You're going to find out its left child and its right child. Is it? So in this case, this is not in the queue anymore. So next you're going to have 78 or 38 and 75. Is it? You're going to add because we are doing level by level. Is it? So that's, oh, I needed to clear everything. Is it? So you're going to add whatever that left. So so it's let's go back to take a quick look at what the what it is I'm going to so it's 55, then 40, 70, is it? Then 38, 42, 58, 75. Anyway, okay, going on, is it? And let's take a look. Okay, so initially we said 55 is in the queue, is it? And then you pull it out, is it? You are going to add what? 40 and 70 in the queue, is it? You're going to enqueue both, is it? And so then when you come to the next loop, the size changes to 2, is it? Because you have 2 nodes in the queue, is it? So you're going to pull the first node out, is it? Oh, sorry, 40 is here. And you're going to output 40 out. And then you're going to add its left and its right. Is it? So 38 and 42 is going to be in the queue, is it? And you are going to get to 70. Is it 71, 70 you get 58, 75. Is it? So you finish this loop when the size is 2. And then next loop, the size is going to be what? It's going to be 4. Is it? So each time it's doubles. Is it? Because it's based on, if it's a perfect balanced binary search tree, is it? Each time the queue size going to be double. Is it? So that's why then you can do level by level printout. Okay, so we can use a queue to implement. Okay. Okay, so that's regarding how do we print out level. And the last one, today we are going to run out of time to complete it. So I'm going to